Hello, welcome to a short lesson on Chapter 6, 6.1, Exponentials, specifically exponential growth and decay. On this first page, if you don't have that, that's okay. I'm going to skip that in this video just for sake of time. It's review of exponential rules, but don't worry, we'll review those quite a bit throughout the unit. All right, first one here. This is just kind of get us thinking in the mindset for exponentials. 9th grade biology, Mrs. Start, of course, tells you the population doubles every minute of some bacteria in a tube. You're starting with one piece of bacteria, and every minute it doubles, fill in the table below. Well, if we start with 1, and it doubles after a minute, of course we have 2. After the next minute, 4, and after the next minute, 8, and so on. Eventually, it's going to get pretty big here. Now, after 5, you know, it doesn't go 6, jumps up to 10. Well, I could just multiply by 2 a few more times and get 1,024. And what about 20? I don't have to multiply by 2 that many times, so I don't really know that right now. And 30, it's going to take me a while to get there. We need a function to model this behavior, okay? And we actually have a pretty standard model for exponential functions. That'll allow us just to plug in 30 and get that number of bacteria without having to multiply 30 times. Okay, so we're going to go into that. Just so you know, what it looks like is f of x, where x is minutes, equals 2 raised to the x. Okay, where 2 to the 0 is 1. 2 to the 1 is 2. 2 to the 2 is 4. 2 to the 3 is 8. Okay, so really we just have to plug in the number of minutes there in this model. We're going to move on. We actually get started into the meat of the lesson. All right, exponential growth and decay. Well, exponential functions are just functions with the variable and the exponent. Okay, so example, just like we had before, if you raise the x, that variable is up in the exponent. And asymptotes, there's asymptotes for these exponential growth and decay functions. Those are always at y equals 0. Asymptote, of course, is just a line that the curve doesn't cross. So we'll have them at y equals 0 for this unit, always at y equals 0. So when we have our growth and decay functions, we usually label that b, okay? So our exponential functions, first let me give you one right up here. The classic exponential function looks like this: a times b raised to the x, okay, where only b is raised to the x. Well, the exponential growth factor is b, and for it to be growth, we need b to be greater than 1, okay? And for it to be decay, we need b to be less than 1 but greater than 0. And so if b is between 0 and 1, that's going to be exponential decay. If b is greater than 1, that's going to be the growth factor. That's going to be a growth factor exponential. Notice that the factor is what's being raised to the variable. So in this case, b is being raised to the variable. All right, so the first example, tell whether the function shows growth or decay, and then graph it. So as we look at that, remember that f of x equals a times b raised to the x. In this case, a is 5 and b is 3/4. So right away, is that bigger than or less than 1? It's less than 1, bigger than 0, so that's going to be decay. Okay, it's exponential decay, the factor of 3/4. Right, and I always just like to plug in, I like to plug in a couple of things, but for this one, let's just go 0, 1, 2, 3, and 4. You go ahead and plug those into your calculator. What you would get out, so 5 times 3/4 is 0. 5 times 3/4 is 1, and so on. What you would get out is the following. Okay, some weird decimals, but that's okay. And then if you graph them, it'll look like this. Okay, and you can see that that's kind of curving slowly. Well, that curves slowly down and always approaches the x-axis, but never actually touches it. So it's continually, as you go off to the right, it continually gets closer and closer to the x-axis without touching it. Okay, of course that's the asymptote, and that's the line y equals 0, or the x-axis. Okay, I'm writing x-axis here, but from now on we'll just always call it y equals 0, because that's technically the equation for the line. So look at domain and range. Well, domain, okay, as far as like what x's left and right do it touch, that's all reals. We could plug in any negative number all the way to negative infinity, or we could plug in any positive number all the way to positive infinity. It would be a really, really small value because we'd be getting closer and closer to the x-axis, but we could still keep going. The range, though, is going to be a little bit different. Range is always going to be bigger than 0, so we can't quite get to 0. Okay, but we can get really close, so that's why it's not a straight bracket, it's a parenthesis. And then the y's can go all the way up to positive infinity here. Is there a y-intercept? Yep, I lost my points a second ago, but 0, 5 would be the y-intercept, so the point 0, 5. And of course, there can't be any x-intercepts if it never crosses the x-axis. There we go, our first exponential. Here's another one. I would go ahead and hit pause and give it a try by yourself if you want a little bit of challenge. You can fast forward to my solutions and skip all my talking and see how you did. Otherwise, just follow along. First of all, that's as we look, y equals a times b to the x. Our growth factor or decay factor would be 1.05. Is that bigger than 1? Yes. Okay, so that must be a growth factor. 1.05. All right. I'll just fill in my asymptote. We know it's going to be y equals 0. So let's do that. Okay, and then I'm going to just fill in some points here. In general, with all these, I go -2, -1, 0, 1, and 2. That's just a personal preference. You get 2 points on the left side of 0, 2 points on the right side of 0. Okay. If you do that, plug into your calculator, you're going to get 2.72, 2.86, 3, 3.15, and 3.31. If you plot them, it looks like this. And we know that it kind of looks like a straight line, but we know by looking at the graph, or by looking at the equation, this is going to be an exponential. So it's going to have that exponential growth curve. It just might be very subtle. You can go ahead and add some more numbers to the right there, plug in some more x's, like 4, 5, 6, all the way to 10. Get more of that curve if you want. I'm just going to eyeball it. So as I draw this, I just know it's going to exponentially grow. I'm going to slowly start bending it up. Okay. Exponential growth. Domain, it's going to be very similar to the last one. Negative infinity to positive infinity. And the range, 0 to positive infinity, just like the last one. X-intercepts, let's go, none, of course. These really aren't going to ever cross the x-axis. And our y-intercept, well, if you look there, where do we plug in 0 for x? Right there. 0.03 is our y-intercept. All right, sometimes we have growth and decay, kind of with percents. This is often used in finances or the appreciation of different assets, interest, stuff like that. So here's the equation we like to use. Y equals, or f of x equals, a times 1 plus or minus r raised to the x. Okay. You need to know what some of those variables mean. So a is equal to the initial amount. R is equal to the rate of change. Okay. And you should be given those in most problems. So, for example, Claire invests $5,000 in an account that pays 6.25 interest per year. Okay, so let's just write this equation out. Y equals A times 1 plus or minus R raised to the X. Okay. Well, what does she start with? Well, her initial investment is $5,000, so that's going to be A. So Y equals 5,000 times 1 plus or minus, and it's 6.25% interest. Now, we can't just write 6.25. That would be 625% interest. All right, we need to move the decimal twice to the left, so 0.0625 raised to the X. And there's our equation. Y equals 5,000 is 1 plus or minus 0.0625 dx. So now we need to decide, is this growth or is this decay? Because we can't have a plus and a minus in our equation if we're going to punch it into a calculator. So the account pays 6.25% interest. That's going to be growth. Okay, we're getting paid. $5,000 is getting bigger, so I'll just change that real quick. There we go. So we just want a plus sign there. All right, equation done. So let's move on to the second part. Estimate after how many years her investment will be worth $10,000 using the graphing calculator table, or just graph the equation. Okay, so if you want to do that, you just have to plug your equation into a graphing calculator. All right, then you look at the table and you see where, for which X, will it cross over 10,000. So it's going to be less than 10,000, less than 10,000. Eventually, it'll cross over and be bigger than 10,000. The Y will. Okay, so the Y's will be less than 10,000. Eventually, they'll be bigger. Okay, that year that it becomes bigger, okay, that's how many years, full years, it would take. In this case, you should get 12 years. All right. It's kind of difficult for me to show a graphing calculator via video like this. So I'll gladly explain that in class. But there's another way to do it as well. Okay, and that way to do it is you plug in your original equation. So Y equals 5,001 plus 0.0625x. You throw that into a calculator. 625 raised to the X. And then you throw Y equals 10,000 also into the calculator. Okay, so that's going to give you two lines on your graph. And you just see where those graphs intersect. Okay? And they actually intersect. That's just a thing you can use, a calculation you can do on your calculator. You can find the intersection of two curves. Actually intersect at X equals 11.43. So 11.43 years. But if we're rounding up to the nearest year, that would be 12 years, okay? Because at the 11-year mark, it wouldn't be enough. We'd still be under 10,000. At the 12-year mark, we would be above. So after 12 full years, she'd be there. All right, and then the last example. A city population, which was initially 15,500, has been dropping by 3% a year. Write an exponential function and graph the function. Use the graph to predict when the population will drop below 10,000. So there's a lot going on here. We got a city. Initially, it's got 15.5. Population of 15,500. It's been dropping a little bit. We're going to write the equation first and foremost. Okay. So first of all, is this growth or decay? Well, if it's dropping, it must be decay. We got to figure out that growth factor. Well, it says 3%. Or excuse me, decay factor. 3%, well, a 3 would be 300%, not 3%. So when we write that as a decimal, it's going to be 0.03. Remember, move the decimal 2 to the left to get rid of the percent. That's our growth factor, 0.03. Let's write the equation now. Y equals our initial amount, 15,500. 1 minus 0.03 to the x. You're more than capable of doing that math if you want. So y equals 15,500 times 0.97x. Okay. Bang, got the equation. Right now I have to graph it. So, well, we can't really have negative time, so I'll start at 0. At year 0, we should have the initial amount. So even without plugging it into my calculator, I know already that's going to be 15,500. If that's what we started with and no time's passed, that's how many people there are still. And then I'm just going to go ahead and count up. 1, 2, 3, 4, and then see where we're at after that. So I'm going to plug it into my calculator and get some numbers real quick. So there are my points. I went ahead and labeled my axes as well, and then just graphed the points on there. Okay, it's kind of a straight line because this is depreciating so slowly. Okay, but if I draw the curve, I'm going to get an exponential that looks like this, which is great. Now we have to figure out when that gets below $10,000. So the best thing to do is just look at the table. If you look at the table, I think that you'll find that after the 14th year and the 15th year, that the population will dip under 10,000. In fact, after 15 years, it's 9,815. So my final answer here, I would say 15 years. After 15 years, the population will dip under 10,000. That's all for lesson 6.1. Hope you enjoy it. And please let me know if you have any questions.